Hello everyone, I'm Martin Brooks and welcome to the third night of Shackleton's Antarctica Now festival. Yesterday our talk allowed us to look down on Antarctica from space as Dr. Mark Drinkwater from the European Space Agency explained the satellite program there. But tonight we're getting a lot more up close and personal with the ice with a perspective from Dr. Mackenzie Grieman, who works to discover the secrets contained in the ice itself. Today, the study of ice cores and what's described as ice memory is a highly respected method, not just of studying climates of the past, but also predicting what's going to happen in the future. Antarctica Now is very happy to welcome Dr. Grieman, who does her work as an ice core specialist and paleoclimatologist at Cambridge University. She's traveled to the Antarctic as part of her work on the Waxwain project, which I'm going to take a deep breath for. I believe it stands for the Warm Climate Stability of the West Antarctic Ice Sheet in the last interglacial. What this basically means is that she's part of a team of scientists trying to work out if the West Antarctic Ice Sheet will melt entirely because of global warming. To do this, they're looking at the clues trapped in ice from up to 130,000 years ago. To explain this in more detail, I'm going to hand over to Dr. Grieman now. We're immensely grateful that you're taking part. I know you've got a big deadline to hit this month, so thank you very much for squeezing it in. Dr. Grieman's also promised to talk a bit about the physical challenges of doing her work, not least what it's like to camp on an ice sheet for 2 months after flying to the remote site in a twin otter. Now, at the end, there'll be an opportunity to ask some questions, but if you use the Q&A function at the bottom of your Zoom screen, we'll pick out some of the questions at the end. I'll hand over. Dr. Grieman, thank you for joining us and welcome.
Thanks. So I have no idea why my video is so red, but just go with it.
No problem.
Hopefully the actual presentation isn't. So.
That looks perfect. Thank you.
Okay. So today I'm going to talk about ice as a time machine, the stories that glaciers and ice sheets can tell us about our past. As Martin said, I'm a postdoc at Cambridge in Earth Sciences, so if you go to the webpage there, you can contact me. So the photo here is showing what an ice core looks like in the drill barrel as we're pulling it out of the ice. So just sort of keep that image in your head while I talk, because that's what we're talking about this whole time. Okay, so first of all, I want to talk about why we look at ice cores at all. And the reason for this is that, as we all know, temperatures are increasing currently and into the future. So on the right here, I'm not sure if you can see my cursor, hopefully you can. On the right here is a bunch of different instrumental records of temperature starting from 1850 and going to present. And these are showing global mean anomalies from the mean 1961 to 1990 level. So the zero here is what was going on in sort of the early latter half of the 20th century. And the main thing to get out of this is that temperatures are really accelerating in the latter half of the 20th century. And we've projected, if you look on the left here, that temperatures will continue to go up. And this figure is showing various scenarios of that increase for the next 100 years. So the red is basically what would happen if we continue emissions the way they are. And the other levels are what would happen if we started to mitigate our greenhouse gas emissions. So because instrumental records can only take us back to 1850, the main thing we can do really from this is just look at what climate has done under those temperature scenarios. So in order to go farther back in time and try to look at what maybe happened during times when temperatures were higher, like what we expect them to be in the future, we need natural records, and that is where proxy records come in. There are lots of different proxy records. On the left here, I'm showing what you see when you look up proxy records on the NOAA website. And if you click on these on that website, you can look at lots of different examples of data from proxy records that's publicly available. So these records span different periods of time. And that's what I'm showing on the right here. At the top is how far back in time different types of proxy records go. And on the bottom, I'm showing the resolution of that record. So that can be anything from seasonal changes to decadal changes to just showing what happened every 1,000 years at a certain location. Then additionally, the third thing that proxy records tell us is what happened either locally, regionally, in a hemisphere, or throughout the whole globe. And I think the easiest record to really understand are tree rings. So we all know from science classes when we were little kids that you can count how old a tree is based on its tree rings. And basically every year you get a new ring, and that tree ring can show you what was going on in the local climate at that area. So trees show you what happened at a particular place going back in time. They can also have fire scars and things like that on them to show particular years that a fire happened at a particular forest. So what we're going to talk about today is a little bit different because we're going to talk about ice cores. And what's kind of cool about ice cores is that there are records that go back as far as 800,000 years. So again, if you think about tree rings, the tree rings will show how long that tree grew. And trees can grow for a few decades to up to 1,000 years. But ice cores can go as far back as 800,000 years. And in some of those records, they're even annually layered. So we're looking at high temporal resolution records that go really far back in time. And a lot of the chemicals that we look at in those records actually show global changes, which again, tree rings can't do. So tree rings are really great if you want to look at what happened at a particular location. And ice cores, which we're going to talk about today, can look at more about what happened regionally or even on a global scale. So where have ice cores been drilled in the past? They've been drilled in lots of locations, particularly in Antarctica and Greenland, as shown here. But I'd also like to note that there are also alpine ice cores from temperate glaciers that go back not as far back in time, but can kind of tell us what was going on at mid-latitudes. So on the left here are just a few examples of ice cores from Greenland. Again, I want to note that there are a lot more than what are shown here. I just didn't want to overwhelm all of us. And on the right are some examples of what have been drilled in Antarctica. So the two that I really want to point out are Dome C and Vostok. And because of where these were drilled, these are the longest ice cores of record, and those are the cores that go back 800,000 years. So why were these locations in particular chosen? These locations were chosen because for the most part, they were on domes. So Antarctica has a lot of local domes, which means that these are the locations where ice flow is the most vertical going down the core. Otherwise, as you go out from a dome, the ice flow becomes more horizontal and you don't get those vertical layers that we really need to get if we want to understand exactly what was happening as you go back in time. So in the center here is where you would expect to decide to drill at an ice core site. And along here, if you were to drill, you wouldn't get those nice vertical layers because you'd kind of be going back in time horizontally. Okay, so what are some things that we look for a good ice core site other than the fact that you're on the dome? Depends on what you want to get out of the core. So if you want to get a high temporal resolution record, so something that is seasonal, like we were just talking about, then you want to have a place where it snows a lot. So a high accumulation, which means there's a lot of snow per year, so you get really thick layers. If you want to go back in time, then you want a location where it doesn't melt here at the bottom. And also there's a lot of ice that doesn't get moved away. And so that's why those Eastern Antarctic sites have those really long 800,000 year records. Okay, so ice cores can tell us lots of things. Today, we're mainly going to focus on temperature, but I also wanted to mention that they have greenhouse gases trapped in them. They're actually our longest natural greenhouse gas records. They tell us about wind speed and transport patterns, sea ice extent, so how much the sea ice geographic region has changed around Antarctica throughout the last few thousand years. Volcanism also increases in sulfate and other chemicals in ice cores that are produced by volcanoes that are transported through the atmosphere and land on the ice sheets and just stay there. They tell us about solar activity because you can look at beryllium-10 in ice cores and other cosmogenic nuclides. Different chemicals that are trapped in the ice core can tell us about how atmospheric chemistry can change. And also there's different chemicals for biological productivity that change over time and get trapped frozen in the ice core. In the center here, this is actually looking at an ice core visually. So not even under a microscope, just looking at an ice core, you can see all of these sort of dots. And those dots are actually bubbles that are trapped in the ice. So as the ice sort of becomes compacted and pressurized, as there's more and more snow piling on top of Antarctica, you get these bubbles, and those can be extracted, and that's how you get the greenhouse gas records. On the very right, this is one of my favorites. This is looking at an ice core at the microscopic level using polarized light. And the number one here is showing the actual ice crystals. So those red arrows are showing ice crystals, sort of, if you look at the ice core from that view from the drill that I showed at the very first slide. So if you're looking down at the ice core from that view at a microscopic level, then you're seeing these ice crystals, and that's the actual water that makes up the ice cores. Number two here are the insoluble and soluble chemical impurities. So along the ice grains and those sort of little tiny black dots there are showing chemical impurities, and those are sort of the things in the ice core that can tell us about volcanism and atmospheric chemistry and biological productivity and all kinds of stuff like that. Number three is the air bubbles. So that's looking at what we're looking at in the center here, but just at the microscopic level. So the big black dots here, those are gases that are trapped in the ice core and extracted. Okay, so today, as I said, I want to focus on how temperature is measured. So this is probably the most sciencey part of the talk. So if it's too much, I apologize, but I think it's really cool. So mainly temperature is measured in ice cores using water isotopes. Now, I do want to give a caveat, which is that water isotopes can tell us lots of different things about climate. But the first thing that they were used to tell us was about temperature. So from your chemistry class in high school or in college, you probably remember that isotopes are sort of the different numbers of neutrons in an atom. So for water, for instance, you can have water, which is H2O, as we all know. Water can have 16 neutrons, the oxygen, or the oxygen can have 17 or 18. The more neutrons, the heavier it is. The same is true for the hydrogen. So the hydrogen can have 1 or 2 neutrons, and that's what you mainly see in nature. Now, how heavy this is and where the heavier versus the lighter water is on Earth changes depending on how hot or cold it is. So if you look here on the right, I'm showing, this is sort of the more central to the left area is looking at sort of near the equator. And then as you go to the right, you get to the poles. And the main thing I'm trying to show here is that the water becomes more depleted as you get towards the poles. So what I mean by that is that the lighter water evaporates more easily here near the equator. And then as you go towards the poles, it rains and it snows and it gets more precipitated out. So more and more water gets rained out as you go towards the poles, and the water that's heavier gets rained out first. So by the time you get to the poles, the water is pretty depleted and doesn't have a lot of those heavy molecules. Now in the winter, it's even more depleted. And so we use this information about the water isotopes to figure out what happened with temperature. So if you don't take anything out of this slide other than the fact that heavier versus lighter water can tell us about temperature, that's really what I'm trying to get across here. And this was figured out back in the 1970s, and we've used it ever since. Okay, so how can we tell from those isotope measurements what happened to temperature? So this is something that was figured out in the 1980s. And on the left here, I'm showing a map of Greenland, and these are a bunch of surface sites and also ice core sites on Greenland. And on those sites, temperature was measured at weather stations, as well as the surface snow, delta 018, or the level of heavy oxygen to light oxygen in the snow at the surface. And what was really interesting that was found out at all of these sites is as you get to warmer and warmer locations, which is here on the x-axis, then you get to less and less depleted, or you get to higher numbers here on the left axis. So there's a linear relationship between temperature and the isotope content of the snow. And so we can use this linear relationship to figure out what the temperatures were like as we go back in time through the ice core. Okay, so this is where we get to the more fun part. So on the left here, I'm showing an actual ice core record. So this is the Epicodome C ice core. So if you remember from when I showed that map of Antarctic ice cores and I said to pay attention to those two on the right, this is one of those. This is the Epicodome C 800,000 year ice core records of carbon dioxide temperature and methane. So on the top here, I'm showing carbon dioxide from that ice core. And in the middle, we have temperature anomaly. So this temperature anomaly was figured out using those isotope measurements that I talked about in the last two slides. And then below that, we're showing the methane record. And methane's really interesting because it's also a greenhouse gas that we also emit into the atmosphere. And though it doesn't stay as long as the atmosphere, it's a lot more powerful and traps a lot more heat than carbon dioxide. So there are a couple things that I want everyone to get out of this slide, if you haven't seen these records before, which maybe you already have. One is that you can see that at high temperature periods, you have high CO2, and at low, and also methane. And at low temperature periods, you generally have low CO2. Yeah, sorry, the temperature's in the middle here. Low temperature periods, you have low CO2. And so there has been a relationship between greenhouse gases and temperature anomalies that we can observe in natural records on Earth for the past 800,000 years. And these natural changes in the Earth, now I don't want to go into this too much, but feel free to ask me about it later, are due to orbital changes of the Earth. And so on periodic timescales, due to the relationship between the Earth and the sun in our solar system, we get these periodic changes in how warm and how cold the Earth is. But we are now changing this artificially. So this is showing the increase in carbon dioxide and the increase in methane that we are seeing due to our own activities. So the 1790 here, ppb of methane, is the 2009 level of methane. And the 386 level here is the CO2 level of methane in 2009. And just for an update, which is something that you can easily look up online, our global CO2 level as of January 23rd was 416, or really it's just going up to near 420 ppb. So we're just increasing and increasing, and that is higher than we've ever seen it in the past 800,000 years. Now, what we're going to talk about in a little bit is why that increase is not quite true in terms of temperature. So just hang on, because that has more to do with the project that I'm going to talk about today, which is the Wax-Wain project. Excuse me. So the Wax-Wain project, which was described at the beginning of this talk, is a project that is joint between the British Antarctic Survey and the University of Cambridge. And it's headed by Eric Wolf at Cambridge and Rob Mulvaney at the British Antarctic Survey. So if you want to read more about them, again, just go to the website. And it's funded by the European Research Council and the Royal Society. The photo here that I'm showing on the left, so a lot of the rest of this talk is just going to be fun pictures, so that's kind of cool. This is where I lived for 2 months on the Antarctic ice sheet. The tents sort of in the background are where we slept, and the tent in the foreground is where we ate and hung out when we had time away from work. Okay, so what is the purpose of this project? This project is sort of to try to get a better understanding of what was happening during the last interglacial, or what we call in science the MIS 5E event. That was about 129,000 to 116,000 years ago. So at that time, Antarctic temperatures were at sort of the level that we expect in 2100. Okay, so if you think about those projections that I showed on the very first slide, this is a very possible projection of what temperatures could be like in 75 years, or I guess 80 years. Okay, so on the left here, I'm showing age. So this is present, and on the left is 150,000 years ago. And again, on the left axis is temperature anomaly. This time, this is temperature anomaly relative to what temperatures were like 1,000 years ago. So again, this is showing the same temperature record that I showed on the previous slide. This is the Epica Dome C temperature record. And this period here with the gray bar is the last interglacial. So during the last interglacial, temperatures were actually higher than they were today, again, at about 2100 scenario levels. One thing to point out is that the cause of the last interglacial obviously was not industrialization. It was due to changes in the Earth's orbit and ocean circulation, like I mentioned before. But still, it is possible that a lot of the ramifications of that temperature change are things that could be seen in the future. And so that is the reason for doing this study. Now, what were some things that were going on about 100,000 years ago when we had this really high temperature? One is that sea level, or global sea level, was higher. So this on the right is showing, from a review study, this Detton et al. Study in Science, that shows 14 different studies, as you see on the x-axis, and their estimation of what global mean sea level was like 100,000 years ago during the last interglacial. And the bottom plot here is showing the contribution to that from the Greenland ice sheet. And again, these are from all of these different studies. And the main thing to get across here is that there are a few different contributions to that sea level rise. The first is thermal expansion, which basically means that as water gets warm, it expands, which is something that we all kind of learned in our basic chemistry classes. And also mountain glaciers, so those alpine locations that I mentioned before, they start going into the ocean, and that increases sea level. The contribution that I just talked about, shown in green here, of about 2 meters back during the last interglacial, is estimated to have come from the Greenland ice sheet. So we can see that in those Greenland records that I was talking about before. Finally, there's an estimation that the West Antarctic ice sheet contributed about, 5 to 6 more meters of sea level rise during the last 150,000 years. But what's kind of interesting is that most of that sea level came from the West Antarctic ice sheet, which is a region where we don't have those really long 800,000 year records. So we don't know, other than by estimates, if that really did contribute to the sea level rise. So that's mainly what we're trying to figure out with this project. I know that's a lot to take in, so please feel free to ask me questions at the end. Okay, so let's talk a little bit more about this. Again, the motivation for the project is to try to figure out if the West Antarctic ice sheet contributed to that sea level rise. So in order to do that, this West Antarctic ice sheet would have had to have collapsed. And also, in so doing, was all of that ice in the water and then increased sea level rise? And did the Ronne ice shelf contribute to that by retreating? Ice shelves are important because they buttress the ice sheet. So that means that they protect the ice sheet from collapse. So if the ice shelf wasn't there anymore, it's much more likely that the West Antarctic ice sheet collapsed. Now, why would the West Antarctic ice sheet collapse and not the East Antarctic ice sheet? So probably the easiest way to think about this is to look at this map on the right where you can see surface elevation. So this is looking at what surface elevation could have been like due to a model during the last interglacial. You still would have had all of this surface elevation on the East Antarctic ice sheet, but all of this white here is projected to have been gone because the West Antarctic ice sheet is actually grounded below sea level, so it has a lot more likely of a chance of getting warmed by the ocean and therefore collapsing. What we did is we decided to drill an ice core here at Skytrain Ice Rise, where that red arrow is pointing and where this model predicted that there still would have been ice during the last interglacial, in order to see if in the ice core there is evidence of that ice sheet collapse. So our approach was to drill a 651-meter ice core at that Skytrain Ice Rise location, and then try to see what happened way back 120,000 years ago, which is predicted to be located in the lowest 30 meters of the ice core. And in order to do this, we had to analyze chemical tracers in the ice core. So before we can go too far into all of that, let's back up and talk about actually drilling the ice core. So here's the map of the ice core locations. So on the left here is just looking at the West Antarctic ice sheet. This green dot with the SK, that is the Skytrain Ice Rise location. And these other dots are possible locations that have been drilled or will be drilled to also try to figure out the same thing. So in the long run, it would be really great if we had this whole diamond and therefore had a sense of what happened in all of these different locations on the West Antarctic ice sheet, or at least maybe if they tell us all the same thing. This is a close-up image of Skytrain Ice Rise. And what I'm trying to get across here is that you can kind of see that this location is its own dome. And because of that, we could drill here and expect those vertical layers like I was talking about before. Also, it's protected from the flow of the ice sheet due to the Ellsworth Mountains, which are the tallest mountains in Antarctica over here. And so because it's protected from that flow, it's pretty likely that this location has an ice core that was preserved during that whole 100,000-year period of time. Okay, so let's talk about the actual fun of getting the ice core. How did we reach the site? Well, we started at Rothera, which is the main British research station in Antarctica, which you probably already know. So this is my boss, Eric Wolf, taking a photo of one of the penguins that we saw while we were there. And we were there for a couple of weeks waiting out the weather to be able to keep flying to our site. So we started out on the peninsula because that is where Rothera is. And then we reached the site via Twin Otter. So this is a Twin Otter airplane. It seats about 6 people, so 2 people in the front and then 4 people in the back. And it's also how we took the ice core in and out of our site, which is what you're seeing here. So the boxes in the front are all boxes full of ice core. And we would have to build our own runway, and then you just sort of take the little plane and go on skis and get from location to location. So we had to stop at a different field site on the way to refuel because it's such a little plane before we got to our site. Okay, let's talk about living in the field. So this is a day when we could still see. So that's why I was able to take a photo. And this is looking at those tents that we lived in. So this is a day that wasn't as clear as those other days. And these tents fit 2 to 3 people. And basically that's where we just went to warm up and sleep. This is our leisure tent. So in the back, you can kind of see how we cooked. And we even had a little bread maker and an oven. And I'm the really cold one in the orange back there. In order to do any of this, we had to actually build the site. So this is all of us building the drill tent where we would drill the ice core. So really, it's just a bunch of plywood on the ground with sort of building a tent like you would build if you go camping, but really big. And then once we built the actual tent structure, so this is after that structure was built, so the white edges here are showing the cloth of the tent. We had to actually build the trench where the ice core was going to be drilled. And so this is my colleague Christoph, who is sort of pulling out the ice at the very surface of where the ice core would be drilled so that we could get started. So once everything was set up, then we had this nice drill tent. And what this photo is showing is what the drill tent looked like when the ice core was actually being drilled. So this is in the very center here, this is the drill. And that drill is going straight down into the borehole and drilling the ice core. And then once the drill, usually it takes about 20 minutes to an hour to go down into the borehole, then it pulls up a couple of meters of ice as shown over here on the right. And then it's on a hinge sort of, and it pulls up and goes horizontal. And then the ice core is pulled out of the drill barrel over here. So to just give you a better image of that, this is Christoph again, and he's pulling the drill barrel out of the drill, and inside of the drill barrel is the ice core. And you saw that in that very first photo that I showed. Okay, so then after the core was pulled out of the drill barrel, it was measured as shown here and cut up in 80-centimeter long pieces. And so this is Christoph and myself looking at an ice core and looking very scientific as we're cutting and writing down all of the measurements of the core. And this is important because the density of the core changes as it becomes more compacted, and you know you've reached the ice zone when that density stops changing. Okay, so after we drilled the core, we had to store it for a while as cold as possible before it's flown out on that Twin Otter. So this is Eric, my boss, again, in the trench that we dug, where we stored all of the cores at very low temperatures, and then they were flown out via Twin Otter back to Rothera. After that, they were taken on a ship all the way back to England, and then next up is to actually make measurements on the ice core. So this is just a quick photo of our lab, or a little part of our lab, and behind this wall is a big freezer, and in that freezer we melt down this 80-centimeter long pieces of core. And from that, we get all of the measurements that we need to try to start understanding what happened during the last interglacial. And so all of the steps that I just talked about, going into the field, drilling the ice core after we camped there, bringing the ice core back, cutting up the ice core, figuring out what we want to do with the ice core, all of that happens before the science. So now we are doing the science part. We have just finished all of these analyses in the lab. So we melted down all 651 pieces of ice, and we're just finally getting to the science part. So what are we looking for in the ice that can tell us something about the last interglacial? There are three key indicators that can tell us about ice sheet or ice shelf change. The first is marine ions. So basically these are sea salt. So when you're at the beach and you get really salty, that sort of, all of that stuff gets taken all the way to Antarctic ice sheets. And it deposits on the ice sheet after it's transported via the atmosphere. And those can tell us something about how close the site was to open water or sea ice in the past. So on the right here, I'm showing this study from the 90s where they looked at how those concentrations changed as you go inland from the edge of the ice sheet. So as you go inland, chloride, which we all know is a really common sea salt because of sodium chloride, decreases as you go inland. And that is true of lots of different marine ions. Secondly, we look at water isotopes, which we talked about before. They can tell us something about temperature. In addition, they can tell us about elevation change at the site, and also how these geographic changes of the site affected the climate pattern around the regional area. finally, my colleague is looking at air content. So just like when you hike up a mountain and the air gets really thin, that air pressure gets trapped in the ice, and we can tell if the elevation of the actual site where we drilled the ice core changed over time, depending on the total air content within the ice core. So now we've measured these things and we're trying to figure out what they mean. In order to do that, the first thing we have to do is date the ice core. And this can be done in lots of different ways that I can talk about after this if you'd like. One way it's done is by comparison to other ice core records. So this is the record of methane. So we talked about methane back when we were talking about the relationship between temperature and greenhouse gases. Methane is a really common greenhouse gas that's measured in ice cores, and our measurement of it in that lab that I showed is the purple. This is the raw measurements that haven't gone through processing, but just from this, you can already see that it looks quite a bit like this yellow record and this red and this blue record, which come from known ice core sites. These asterisks down here are little tie points between the two sites that I chose to try to figure out the relationship between the ages of our ice core and the patterns that we see in those other two cores. And that's one way that we're going to be dating this ice core. Okay, so with that, from there, we have measured all of those ions and the water isotopes to try to figure out what was happening. So currently we're at this stage of dating the ice core, and after that, we're going to try to figure out what happened to the ice sheet. Okay, so with that, that's everything. If you want more information, there's a Royal Society YouTube video called Adventures in Antarctica, Drilling for Ancient Ice about our project. So if you want to listen to me talk even more, you can go there. If you're just interested in ice cores and how they work, a really good book that's very readable is The 2 Mile Time Machine, Ice Cores of Climate Change in Our Future. It's written by Richard Alley, who's a famous ice core scientist. And we also have a Twitter account about our site, and that's @waxlane. And obviously you can go to the British Antarctic Survey or the Cambridge Earth Sciences website to get more information. And that's everything. Thanks for listening. And I'll stop sharing my screen.
Oh, Mackenzie, that was fantastic. Thank you.
I don't know why it's so red, but that's
fine. My O-level science wasn't that good at keeping up with some of the middle bits, but I get the.
Oh, I'm sorry.
No, that's fine. I mean, that's why we wanted you here. And it's very interesting. We've got a very broad range of questions. Some I think are very technical, which we're going to ask you, and then some others which are less so. Let's start with this one. This is from Peter in Paris. What's been the biggest eureka moment for you since you've been working on the Waxwayne project?
Sorry, the biggest what moment?
Eureka moment.
Eureka moment.
Well, have you had one?
Embarrassingly, I think it was when everything worked in the lab for the first time. Because that was a struggle. So those instruments that I showed in the lab, well, for me, I wasn't in charge of the drilling, I just helped. But in the lab, we were trying to get 11 different instruments to work at the same time. So when we got that to work, that was pretty exciting. And also when we got to the bottom, and as you can tell from that methane record, and also from the isotope record that we're working on, we know that we've gotten to the last interglacial. So that's really big because this is one of the first West Antarctic records that goes back 130,000 years ago.
And to be doing that, yeah, I mean, it's just incredible to be able to put all that kit together in that drilling tent in the middle of absolutely nowhere on that ice sheet. Must be quite a feeling, a satisfying feeling of achievement.
Mostly cold, but yeah.
Yeah, exactly. We'll come back to what was it like living there later. But so a question from Sebastian Copeland, who's actually talking tomorrow. He says, I assume that you are referencing the Milankovitch cycles when you refer to the changes in orbital cycle as they relate to changes in temperature over the last 800,000 years. Could you help us understand why the cycles affect not just temperatures as the planet moves away or towards the sun, but also the GHG concentration? And I wonder if you could explain to everybody what the GHG concentration is as well, please, because I can't help you there.
Okay. Yeah, I should apologize in advance. I'm very used to scientific audiences, so I'm sorry if it was too fast. No. But anyway, Okay, so GHG is greenhouse gas. And the reason people say GHG is because everyone always talks about carbon, which obviously is important. And carbon dioxide and methane are the forms of carbon in our atmosphere that alter climate. And the reason, okay, so there's two points I want to get across here. The first point is that we're still figuring out whether or not CO2 lagged temperature or temperature lagged behind CO2. So what that relationship is in the past is something that scientists are working on. The second thing I want to talk about is called carbon feedbacks. So yes, orbital cycles are the natural reason why we see temperature change. And when the temperature changes, that causes feedback mechanisms on our planet. And those mechanisms release carbon or uptake carbon dioxide from the atmosphere. So I don't know how familiar everyone is with the carbon cycle, but basically each reservoir of the Earth, so the atmosphere, the ocean, the land, they all have different forms of carbon in them. And as the temperature changes, the amount those reservoirs are able to store of the carbon changes. So for instance, everyone hears about if you plant a tree, you're going to help the planet. Okay, so that depends on where the tree is, but let's not get into that. Let's just talk about how trees have carbon in them, okay? So as it gets warmer, you change how long trees are able to grow, whether or not they die, all of that kind of stuff, and that releases carbon into the atmosphere. That carbon is then taken up by the ocean, and the amount that the ocean is able to take up also depends on temperature. Then if you change the amount of carbon in the atmosphere, carbon dioxide or methane in the atmosphere, you're actually changing how well the planet is able to, or really the atmosphere is able to trap heat on our planet or not. So it's all about cycles. Things go up and things go down based on temperature, and then the temperature goes up and down based on all of that. So yeah, if you want more information about that, I can send you in the right direction, but just think of it as our Earth has cycles and all of these different attributes change those cycles.
Thank you. I mean, there's one that's sort of very much linked to that I think I know the answer to, but you'll give us the authority on it. So from Felix Belloin, I think you say it, could the cyclical orbital shift play to our advantage before emissions send the temperature soaring?
No.
No.
Sorry, I should say more. Okay, so
no,
basically what we're seeing is unprecedented, not in that we haven't seen temperatures that are this high before, because as I said, 130,000 years ago, temperatures were likely higher than they are today, but we've never seen greenhouse gas levels this high. So we only know what that's going to do based on models. We can use these proxy records to try to figure out what the temperature change that causes could possibly do to the planet. But we've never had this much carbon dioxide in the atmosphere. So again, like I was talking about those reservoirs, right? So the amount of carbon on Earth doesn't change, but where the carbon is on our planet does. And we've just never had this much in the atmosphere before. So yes, the cycles help, but another way to think about it is cycles are on 1,000-year time scales, and the warming that we're seeing is happening on less than decadal time scales.
Great.
So it's going to happen fast.
Yeah. Okay.
Not to scare everyone, but
well, a positive one, a very, very different kind of question from 10-year-old Phoebe Tillard. Were you the only girl on the team? And how do I become an Antarctic scientist like you when I'm older?
Okay. First, I was not the only girl. I have been on research projects where I was, but it was nice not to be. There were 2 other girls on the project. One of them is now working for a company, but she was also a researcher at the British Antarctic Survey. And the other one is currently getting her PhD at Cambridge. And there are lots of girls working on the lab part. So they didn't go to Antarctica, they've gone to Antarctica, but not for this project. And a lot of the people working on the lab side of it are girls, women. How do you get into it? That's a long story, but basically just keep taking science classes. So when you get to college, or sorry, university, I'm American. When you get to university, just keep taking college courses and sort of stick to science, and you can get there. I actually was a social science major at university, but I went back to science afterwards. So you can do it. You just have to stick with it, and it can be hard. So, but it's worth it because you get to go to cool places.
Absolutely. It's actually a question
Literally.
I can answer from Richard Anthony Morris. We'd love more information on the carbon reservoirs. Also, are these talks going to be rewatchable? Yes, they are going to be rewatchable. This one will be on, like all of them, will be on the shackletonlondon.com website from about 11 o'clock tomorrow morning. And then if you actually go back through Mackenzie's talk, there was a slide that you brought up with more references on there. So we could, you get more information from there. Question from somebody called Acacia. After you remove the core, take down the camp and head home, what happens with the hole you drilled in the ice sheet?
Oh, that's a good question. So it depends on the project. Some projects, they let the hole close up. Some projects, they put fluid in the hole so they can go back. But I guess one important thing is that we actually have to keep putting drill fluid into the hole to keep it open, so that you can keep drilling over time. It's really cold to do it, but every week we had to actually put drill fluid in the hole to keep it open. So some sites still have drill fluid in them, and it's kind of an environmental impact thing to try to figure out, and the science that's being done there. But some holes are just allowed to close back up.
Sure. And I'm sorry if you said, but I personally missed it. When you were drilling right down to the 800,000 level, how long does it take to drill that far down?
Okay, so just to first note, our core only went back 100,000 years. Those 800,000 year cores are different. It depends on the drill. It depends on the project. It depends on a lot of things. Our project was unusual in that we drilled a whole 600-meter ice core in 3 months. A lot of those other projects I was talking about, you know, they go 2 miles down and they go back multiple seasons. So a really famous one is the Waste Divide ice core that's in the middle of West Antarctica. And I think, I don't remember how many seasons it was. I think it was 3, but that had like a lot, like 40 scientists and big sort of drill tents and things like this. Our project was, you know, under 10 people. So each project is really different, but a lot of ice cores are multiple seasons, but you have to go in the summer season because then it's not pitch black.
Absolutely. Question here from Helen. I get how you can find out about air composition from ice cores, but wind speed, how does that work?
Oh, okay. How do I? Okay, so wind speed may be tougher, but transport of, okay, so let's see. There are isotope models that scientists use, and they also use satellite information to look at how winds get to different locations on the site and how that changes the isotopic composition that you see at that particular site. So basically you have to take your data and go backwards with computer codes and things like that to figure that out. It also just comes from correlation. So wind speed maybe is tricky, but if you think about big patterns, so everybody knows about El Nino, right? So there's big patterns like that all over the globe, and those patterns change how wind is transported to different locations on Earth. And so that changes the locations of those water sources that we see at the site. And that's actually looked at using a bit of a different parameter, but we could talk about that offline, but it gets complicated.
Okay, last one from Stefan in Stockholm. So how do you like living on the ice sheet? Do you suffer it for your science, or do you actually get a kick out of it as well?
I'm a bad person to ask about this because I actually had to leave because I had some nerve damage in my feet. But I enjoyed it to an extent. It's very planetary. Sometimes it's really, really beautiful because you can just see for what seems like miles, and you can see, like, we could see the Ellsworth Mountains on really clear days. And it's just one of those experiences that you really can't get anywhere else. Like, even from Rothera, even though there's like semi-permanent buildings there, it's really an unusual experience to walk outside, and there's seals and penguins and icebergs and all kinds of stuff. And probably one of the best experiences is looking out the Twin Otter, and you can see sea ice and all kinds of things. It is very cold. There were times when I was very cold, and I run pretty cold, so that didn't really help. And also, you just have to decide that it's kind of like being in lockdown. You're not going to see your family or friends, or be able to really communicate with them, because we just had like satellite phones and that kind of thing. So yeah, you just sort of have to decide that's what you're going to do. There's people who go down to Antarctica for a year at a time. So there's people who winter over and all of that stuff. So my experience was really only a couple of month period.
Yeah, I mean, the feeling, I've only been to the peninsula, but the feeling of remote isolation is pretty intense there. And then, when I think about my colleague Lou Rudd, who's actually trekked twice single-handed, well, actually once with a team and the second time single-handed across the whole of Antarctica from one side to the other, 56 days.
Yeah, I don't recommend doing that.
And he's the sanest guy I know. It's unbelievable. I don't know how he does it. Okay, well, look, that's absolutely fantastic. Mackenzie, we've really, really enjoyed it. Fascinating evening. And I know from the questions and some of the people that we've been seeing on the Q&A that there's obviously some pretty hardcore scientists in there, as well as some people with general interest. So that's been fantastic. Thank you very, very much. Tomorrow's Antarctica Now from Shackleton, we're very excited to have, as I said earlier on, internationally renowned climate advocate and polar photographer Sebastian Copeland, who's going to come and talk to us about his work and about using photography to influence opinion and awareness, and about his most recent book, Antarctica, The Waking Giant. So really hope to see a lot more people back with us tomorrow at 6 o'clock. Thank you very much for watching Antarctica Now from Shackleton. Thank you again to you, and have a good evening, everybody. Thank you.
Yeah, thank you.
Thanks again. Bye-bye.